Sorry about that. I guess I accidentally disconnected myself. I don't know at what point I did. Um, so yeah, so going through the stuff, right? So what I did, right, is you can change the frequency, right? You can rearrange that equation so that you can basically change the speed of light, right? Where it's typically in meters per second, you can change that into nanometers per second. And all you have to do is just simply multiply it by 1 times 10 to the ninth. And so you get that value, right, which is then 2.997 times 10 to the 17th nanometers per second, right? That's the speed of light then in nanometers. So all you have to then do is take that, divide that by the wavelength, and then what you get is the frequency in these cases, right? And so you can just work your way through the table right there. Now the next question is related to essentially, right? If you expose the metals to if you expose the metals to, let me just see something real quick. The just to make sure that it's actually on and running. I'm just checking over here. Okay, it is, but it all got messed up. Right. So the next part of the question is you work on you the next part of the question is asking, calculate the velocity of electrons released from each metal when exposed to 430 nanometers of light. So the thing that you have to think about and the thing that you have to work on there is first figuring out which metals are actually going to release electrons. And then the next step is figuring out what is the energy difference, right? How much energy is actually going to then get transformed into kinetic energy with the electron. And then once you know the kinetic energy of the electron, you can then calculate what the velocity is. In those cases. So if we're looking at 430 nanometers of light, the thing that we then have to now do, right, we can go a step back and we can look at the table that we have here, is we have to find all of the wavelengths of light, right, where the work function is actually, the wavelength of that work function is higher than 430, right? So the only ones that are going to, release an electron in this case are going to be calcium, right, because the wavelength of release is 432 nanometers. We're also going to have sodium, and we're going to have cesium, and I believe that's it, right? It's going to be only those three. Let me just make sure that that's what I put on the key. Yeah. Right. So it's only going to be those three right there because their work function, right, that energy, the wavelength of that energy is higher than 430. Anything that has a wavelength that it requires that is lower than 430, right, isn't going to release an electron because you're not putting in enough energy to pull that, have that electron get ejected in these cases. And I should stop flaring around with the pen because it'll probably disconnect. So that's why, right, like titanium isn't going to work, iron isn't going to work, uranium isn't going to work, silicon isn't going to work, right? None of those have too high of a work function, right? They require too much energy compared to what that specific photon is able to deliver. So the way that we approach this now, right? So if I'm just going to copy these things down, calculate the velocity in these cases for 430 nanometers of light. The next thing that we want to then do is transform 430 nanometers of light into an energy unit. And so, going back to that equation that we had used, right, if we're going to go and we're going to look at, electron volts, we can just easily, do that there. So if we're going 430 nanometers of light, if we're looking at the energy in electron volts in this case, right, that's just simply then going to be the 1240 nanometers per or what's the equation that I'd used? 1240 Should be nanometer EV. Just as a note. Because then the units don't cancel. But whatever. Right, so it's 1240 nanometers per EV, or EV, over lambda in nanometers. So if we plug in, right, 1240 nanometers dot EV over 430 nanometers, nanometers cancel. What we get is 1240 divided by 430, and we have 2.88 electron volts, right? So that's the energy of the photon in electron volts, right, is 2.88 eV. So if we had done that beforehand too, right, we could have just simply seen right here, right, 2.88 eV is higher than the work function of calcium. It's higher than the work function of sodium. It's higher than the work function of cesium, right? It's not high enough for all of the others here, right? It's not high enough for titanium, iron, uranium, or silicon. So now the question is, right, for each one of those cases, right, what's the velocity going to be? So what we have to do is we have to calculate what the energy difference is, right? Because we're going to use up, you know, whatever the work function is from that energy of that photon to release the electron. And then the remaining energy is all going to be, you know, the maximum amount of it is going to be translated into the velocity with which that electron is actually ejected. So if we use calcium as an example, right, we have the work function is 2.87 EV, right? We have the wavelength right here, and so that then that energy difference that we have is going to be, you know, 2.88 EV minus 2.87 EV, which is 0.01 electron volts, right? So that's the energy difference between the two of them. And so we can, you know, assume, you know, that, you know, hypothetically, if all of that energy was directly related into kinetic energy, right, that electron would then be moving with, you know, a speed related to 0.01 electron volts. Now, the way that we then calculate the speed is if we go back to the equation that we have at the beginning, right, we have to refer to, you know, the relationship where we have the kinetic energy, right, KE, is equal to 1/2 mass times velocity, right? Squared, right? So we know what the kinetic energy is, right? We're going to simply, you know, go on the assumption that all of the, you know, remaining energy is being transformed into kinetic energy for this electron. We know what the mass of an electron is, right? The mass of an electron is equal to 9.1094 times 10 to the negative 31 kilograms. And then the velocity is what we're going to be solving for, but the velocity is then going to be in, right, meters per second in these cases. Now, one thing that you can prove to yourself, right, is that the kinetic energy and then the mass and the velocity all relate to each other. Is that, right, the kinetic energy has to be in joules, right? So it has to be in joules, and that's because a joule is equal to a kilogram meter squared over second squared, right? That's what the units are for a joule. So the next thing that we have to then do is convert that energy difference that we have here into joules, right? So if we just simply take this and multiply it by 1 times 10 to the, what is it, negative 19 joules per electron volts, we get that energy difference is 0.01 times 1 times 10, not 1 times, it's 1.60218 times 10 to the negative 19 joules per electron volt, which gives us 0.01 times 1.60218 times 10 to the negative 19 joules per electron volts, right, gives us 1.60218 times 10 to the negative 21 joules, right? Because electron volts cancel in these cases, right? So that's what our kinetic energy is in joules. So that's going to be then equal to 1/2 times the mass times the velocity squared. So the mass is going to be the mass of the electron. So we have 1/2 times 9.1094 times 10 to the negative 31 kilograms times velocity squared. Right, so we have that right there. So now if we want to get it to velocity, right, we have velocity is going to be equal to, velocity squared is going to be equal to 1.60218 times 10 to the negative 21 joules over 1/2 times 9.1094 times 10 to the negative 31 kilograms, right? And so then that 1/2 can just simply flip up here. So that's just, times 2 in this case. And then because we're just trying to get to velocity, right, all of that's going to be under square root. So if we take that and plug that in, right, so we have the square root of 2 times 1.60218 times 10 to the negative 21 divided by 9.1094 times 10 to the negative 31 gives us a value of that I have that's different from what I have right there. 1, 2, 3. So I got this time around 5.93 times 10 to the 4th meters per second, whereas what I have on the key is 6.81. So I'm just wondering what the difference is between the two of them, and it could just very well be something related to energy conversion somewhere along the way. Because everything else is correct, right? Because you have the energy of the photon minus the energy of the work function. And then you can convert that into joules. And then once you have that, right, you use that as the kinetic energy. So it's 1/2 times the mass, which is 9.1094 times 10 to the negative 31 kilograms, times the velocity in meters per square, velocity squared. You rearrange all of that. So times 2 divided by the 9.1094. So all of that should be right. So it could very well be right that there's probably, what I was using here was maybe had, more accurate or so within the differences that we have, right? Because I guess one thing I could do is just see if I were to go through the whole steps of doing everything in joules, how much of a difference we would get for that. So if we were to do this in joules, right? So the first thing, if we were to do the energy of the photon but in joules, is going to be 6.626 times 10 to the negative 34 joule seconds times speed of light, so 2.9979 times 10 to the 8th meters per second, right? And then divide that by the wavelength, and I'll just keep that in meters, so that'll just simply be 430 times 10 to the 9th meters, or 430 times 10 to the negative 9th meters. And so that energy is 6.626 times 10 to the negative 34 times 2.9979 times 10 to the 8th. Divide that by 430 times 10 to the negative 9. Gives us the energy in joules as 4.620 times 10 to the negative 19 joules. And so if we were to convert the work function for calcium, right? So that's 2.87 electron volts. So 2.87 times 1.60218 times 10 to the negative 19. that comes out to being 4.598 times 10 to the negative 19 joules. And so then the kinetic energy in that case will be 4.620 times 10 to the negative 19 minus 4.598 times 10 to the negative 19 comes out to 2.2 times 10 to the negative 21 joules. Right, so we have that, which is, yeah, so that's probably where like the discrepancy and the difference is coming from, right? Because the kinetic energy that I had gotten up here, where I had just simply done the electron volt difference, was, you know, a difference of 0.01 electron volts, which if you convert that into joules comes out to 1.60218 times 10 to the negative 21 joules. Whereas if you convert everything into joules first and then do the subtraction, what you get then is 2.2 times 10 to the negative 21. But in terms of, right, if I were to just simply, you know, I guess if I were to use sig figs, right, properly, both of them would just come out to being simply 2 times 10 to the negative 21 joules. I would have gotten the same answer. But right, there's always going to be a range. So in terms of like thinking about, you're probably like, oh, what about the exams and stuff like that? There's usually like there's typically a range, right, that we look at, and it's primarily the work, right? So if all of your work matched what I did right here, and then your value, you know, was, you know, slightly different from what I had like in my key, right, you'd still get the full points, right? Because more than likely it was just like very, you know, as you can see right here, right, simply going, you know, doing the subtraction in electron volts versus doing the subtraction in joules gives numerically different answers, and that has to do primarily with the difference in you know, the thresholds of what everything is, right? Because we're only looking at 3 sig figs initially for the subtraction, but then when you're doing the subtraction, you only end up with 1 sig fig technically, right? And that, you know, basically holds the same for you know, the other subtractions as well. So that's where that discrepancy is, in case, you know, you did it one way or the other, you know, where that difference in energy is coming from. And then you just do that same thing, right, for sodium and cesium as well, right? You just do that same process. You know, do the subtraction either with electron volts or joules, but you have to make sure that you're, you know, that you converted the wavelength into energy, and that's when you do the subtraction, and then that remaining energy that you have, right, gets converted to kinetic energy. That kinetic energy then gets plugged into the 1/2 mv squared, and then you just simply solve for velocity by rearranging everything in that case. And then, so part D, without performing any calculations between titanium and iron, which would you expect to release an electron with a higher velocity when exposed to 260 nanometer light? So we're looking at titanium and iron. If we just look here, right, titanium and iron, what we have is, right, in the case of titanium, we have a work function of 4.33 electron volts. And in the case of iron, we have one that is 4.67 electron volts. And so that tells us that iron requires more energy to release the electron, which means that there's going to be less remaining energy left to be converted into kinetic energy to you know, shoot out that electron at a higher velocity. So, you know, the lower in energy the work function is, you know, if as long as the photon stays at the same wavelength, right, the velocity is going to be higher. So the titanium is going to eject the electron at a much higher velocity compared to the iron. And we can just simply do that, you know, figure that out by just looking at the wave function energies. Final question, right? We're talking about the photoelectric effect. Use the space below to draw a picture illustrating the effect, right? So if you have your metal surface here, and then you have, you know, your photon coming in, right, that gets ejected here, right, as an electron. And that's what it looks like, you know, as a simplified cartoon drawing. So that is the first problem, which I spent over an hour working on, primarily because I kept on messing up on the derivation. All right.